Hi, welcome to join the time synchronization session in OCP 2020 Networking Hardware Workshop. Today, I'm going to talk about testing and implementation of time synchronization of open networking platforms. I'm Samuel Fu, PLM from Delta Electronics. My partner, Vivian Shi, is our front-end sales located in Europe. Please feel free to contact us after this video if you have any question or have any chance for cooperation. Nowadays, 5G technique has been discussed widely due to its high bandwidth and low latency. In order to achieve this goal, the base station and antenna side must use several techniques like carrier aggregation and beamforming. In order to achieve these two techniques, the timing between base station and antenna must be alignment together. The telecom organization, just like 3GPP or ITUT, have defined an overall timing budget for telecom backbone. In this slide, you can see the overall budget is 1500 nanosecond end-to-end. You can see it separated into three sections. In source is for 100 nanosecond for PRTC and Telecom Grandmaster, with 200 nanosecond networking variation. In the right hand side, it is for application section. It has 215 nanosecond for short-term holdover and 115 nanosecond for application. In here, it remains 800 nanosecond for boundary clock section because boundary clock need to cascade together in order to provide connection for whole networking. ITUT have defined several different classes for boundary clock in order to classify different level for boundary clock. The basic idea is 8 class need to within 15 nanoseconds per node. It means if you cascade 11 nodes with 215 nanosecond link asymmetry, you could still remain in the time budget. For B class, for each node is within 20 nanoseconds per node, you can cascade 21 node with 380 nanosecond link asymmetry. So you can see if each boundary clock could provide this timing error, you can cascade more nodes still under the overall timing budget. So the BC, TBC is tighter. It will give you more flexibility in the network deployment. We are always talking about time sync, but what to sync? In here we have frequency, phase, and the time to be synced. But what's different? For frequency synchronization, if you could not let your system fully sync in frequency, then it will accumulate the time difference little by little until your system cannot tolerate it. And the second one is phase. In here, we assume that your frequency is fully synced. But now you will have made another problem, that is, they may exist a phase error here. You will continuously to living in your system, especially when you need to cascade many nodes together. So the phase error will accumulate through many nodes cascaded. And for the time, you can see the minimum unit here is for seconds because it is relatively long range in timing. So it is much easier to deal with maybe I2C system or SM bus. So here, I don't think time synchronization will be a problem in our topic. So the major target is frequency sync and the phase sync. And in here, we are aimed to deal with frequency sync through SyncE and the phase through 1588. We will introduce in the next page. Our target product type is for these three. The first one is EEC clock, Ethernet Equipment Clock, also known as SyncE. It has a PLL inside in order to reproduce the frequency from the source. So in the application, it must cascade it with a frequency source and pass to the next level who need the frequency sync. And for another two is boundary clock. And here is separated into two types for partially time support and fully time support. In the partially time support, we provide a center timer in order to deal with phase synchronization and the time synchronization. In the application, it is much flexible because you don't need the whole networking support time sync. You can use two partially time support boundary clock to achieve end-to-end synchronization because the timing packet can through the unknown networking and then send it to the target, and then the target side can receive it, then it could achieve time sync. For the last one is 40 time support boundary clock. We have a PLL inside and a time center inside, so we could achieve a frequency, phase, and the time synchronization. So in the application, because we have a physical link from PLL, and we also have a PTP packet to deal with frequency and phase. So when sometimes the packet could not achieve the target, so it could still hold over through the physical link and also very stable for the overall result. What's different between SyncE and PTP? In here, you can see we can imagine that SyncE is combination of different gears. You need to combine and connect all the gears together in order to let the whole frequency transmission work very well. And in your duty, you must have a PLL inside it, and the PLL will indicate three important status for free running, lock, and holdover. For the free running state, it means the PLL have not reference to any input clock source. And for the lock status, it means PLL already absorbs some master clock source, and it can output by the PLL with almost the same frequency as the input. And for the holdover state, it means that PLL is losing the frequency reference source, and it is counting on the previous reference, trying to holding an similar frequency as the previous reference clock. So when you need to implement a synchronization Ethernet, you need to notice that the hardware frequency path is working very well, and you also need a PLL inside it. So in that SyncE system, if you take away one component, just like you take away a gear here, so rest of all system will losing the frequency reference source. So we need to through a physical link in order to achieve frequency sync. For the 1588, it is a precision time protocol. It means we must use the message to communicate in order to achieve a time synchronization. So here you can imagine that is a stamper in the time source side. It will stamp its central time into that packet, and then send the packet to our DUT, and then the DUT will catch that timestamp and read out that TOD value, time of day value, to correct the central time in the DUT. So the following figure here for transmission T1, T2, T3, and T4, it is for calculate the path delay in order to compensate to get the real time for the T1. So in 1588, it's a little bit complex than SyncE because it needed hardware to support in what we call a DCO, digital control oscillator, in order to let the software fine-tune little by little to achieve a time sync. So you needed a hardware skill to implement the overall system, especially in the integration. In the time synchronization, here are several combinations of timing key blocks. In the aspect of Mac, it's separated into two parts. The first of all is external 1588 solution. We also call it broad-sync interface solution. And another is Mac internal solution. We'll call it broad PTP solution. For the external solution, you can see we have two components here besides the CPU and the Mac. Then here, Mac is the key role here because it is our packet switch, and it also needs to do the time stamper. It needs to stamp time for the next level. It also needs to receive the timestamp from the master side. So the CPU is our system host, and it also needs to run a 1588 server call on it. So something about time sync is on PLL. PLL must control the frequency and control the phase. And we have an FPGA here to translate the precise frequency and the phase into broad-sync interface in order to feed it to Mac. Because the timing is outside the Mac, so that is what we call an external 1588 solution. For SyncE, you can see we only keep an PLL with it because in SyncE you don't need to do phase sync, so you don't need a FPGA to translate it into broad-sync interface, and the Mac don't need to do a timestamper. The CPU don't need to run in 1588 server. And for Mac internal solution, you can see the CPU do not doing some other complex things because all about timing synchronization and packet forwarding is working on Mac. Mac will be the packet switch, and it runs a broad PTP function, and it also a timestamper. We still keep a PLL outside the Mac because we running an 1588 for 40 time support, so we use a PLL to maintain the frequency, and the phase and the time we will keep in the Mac for internal solution. So how do we test 1588 performance? We use it with a Grandmaster. The Grandmaster will be a timing source here, so we use a Ethernet connection with our DUT. In here, we use the Delta cell-side gateway router, AGCV208S as an example. You can see the green line in the middle. That is a PTP packet transmitted in the 1G or 10G interfaces to transmission 1588 packet in order to achieve time synchronization. But how do we measure it? You can see another yellow and the blue line here. That is the 1 pps output. It is hard to measure the central timing of the machine from the packet. So we will use a 1 pps to measure it, because 1 pps indicate the nanoseconds rollover point for each system. This is the most way we use when in the real experiment. So you can see the 1 pps is continuously close together and then keep in a relatively stable distance between these two. In here, I will introduce several important test items. In the ITUT boundary clock spec, it provides 5 major test items in order to discuss the DUT and the whole system's relationship. For the first one, it is noise generation. It means the overall system will provide us a noise-free source to the DUT. To observe that DUT will generate how much noise to that system. So the first one is for protect the overall backbone system. And second one is noise tolerance, because in the real situation, the system will have a noise source. So second one is for protect our DUT. It will observe will our DUT receive and tolerance that noise, or when we receive the noise, we will shut down or maybe could not work correctly. And the third one is noise transfer. And here, the tester or the system will provide us several different kinds of noise timing source, and to observe can we eliminate those noisy source, or even we maybe will amplify the noise. And next one is holdover, because when the real system, you could not guarantee that the timing source will 100% providing the source to you. Maybe you will have sometimes it will shut down accidentally. So in this time, we must make sure that we can always keep the stable timing to the next level, because the boundary clock have an important feature is we have a timing center inside it, so we can retain a stable time here even we do not receive the time source from the master side, so we can keep the system more stable in timing. A last one is transient response. Because here we have several different timing source, so sometimes when the source is disappear, we must quickly to switch to the second source. So when the switching happen, will our timing have a change in response here? Will it jump a little bit to impact the whole system, or it will keep a very stable here? That is the 5 major items. Before we go to the real system, we can do it with a tester named Paragon X. So our product already passed these 5 test items. In the following several pages, I will demonstrate it, several important things, just like noise generation, noise tolerance, and holdover as a reference to you. So as you can see here, this page we use our SS switch AGC 7648 SV1 to test noise generation. So you can see the result for the 1 pps. It is very stable when we receive a noise-free source. And also there's a packet two-way time error. You can see they are less than 5 nanoseconds. In the ITUT G.82 and 73.2 boundary clock, it defines 3 levels for A class 15 nanoseconds, B class 20 nanoseconds, C class for 10 nanoseconds. We are past the C class here and even approaching to the D class. And for the next item is noise tolerance. You can see we have used the paragon X to input a noise pattern, a different sine wave combination to our DUT, and it could still remain in a very stable status and do not show any error in our system. It did happen a little bit influence, but not too much here. Still keep in the 5 nanosecond. And for another one is hot over test. As you can see, when we stop the packet transmission in around 9,000 seconds, and it could still keep within 125 nanoseconds in 1 hour, and within 1,500 nanoseconds for 4 hours. And for another one is variable temperature. ITUT has defined for the reference temperature profile. We think sometimes the thermal shock is very important to that system. So we decided to do it ahead. So you can see the red line here is the thermal chamber record. For the 1 pps line, you can see it is almost alignment to the temperature variation, and we run in this process for 43 hours. It could still maintain within 5 nanoseconds. It indicates that our system is very stable even when the thermal shock, because the timing is hugely depends on the stability of the oscillator. But here we use OCXO, oven control oscillator, in order to stabilize the thermal shock for the timing system, so we can gain a very nice result here. So the last one is boundary clock cascaded testing. Our product is aimed to doing a boundary clock. So at the end, we need to cascade all the system together. So here we cascade our 2 type of machine with tested paragon X. Our first machine is SS switch AGC 7648 SV1 and our cell side gateway AGC V20AS. These 2 switches is possible to connect with 5G NR and for the LTE, and even to 2G or 3G system through our 10G or 25G or 1G Ethernet. So here's the result. When we cascade these 2 machines, we measurement the synchronization Ethernet and the packet two-way time error as a result here. You can see the SyncE have a 2 nanoseconds differentiation here, and for the two-way packet time for two node cascaded, it is for 6.58 nanoseconds here. It is very stable for the overall result. So last one is our conclusion. I think 1588 will be trained in time synchronization because it has below advantage. For the first one is 1588 is an in-band time synchronization. It means that you can use this wiring. You don't need to use a dedicated system, just only for timing synchronization. And the second one is because here we use the boundary clock to achieve a 1588. So it retains a center time here with a very stable OCXO. So it could hold over very stable. So it means you have a highly stable system when use a boundary clock. And last one is it is an extremely precise because nowadays our boundary clock is aimed for 5G's application and for TSN. It is very tight requirement in timing. Now it is being defined in D class for 5 nanoseconds. So I think it is suitable for telecom communication. So maybe it is much critical than other systems like a power station or some automation requirement. And maybe it will several different requirement in data center, but I think in the future it will be discussed. And the second conclusion is, according to the single box and the cascade test result we introduced previously, you can see our noise generation, our noise tolerance, however, and the temperature shock is very stable here. And also you can see our cascading test is also can keep in the same level. So thank you for joining this section. Here this page introduce our product. You can contact us through that web page or contact me through the OCP. Thank you for joining today.